Today we'll be starting chapter 9. We are basically skipped chapter 8, and that we are going to cover it towards the end of the class because I mean it's some different topic that's coming in the middle, so it would be better if we cover it later after the end. Is there any question before I start? Okay, then we can move forward and discuss today's topic. Coding and benefit of doing Cascode. Cascode, if you remember, it looks like we basically have a source at the impedance of the amplifier. So the source is not grounded, but the source has an impedance that is basically either RS or any impedance. And we like to have this impedance to be large in order to get larger output impedance that we want to have here. We previously derived the impedance for R out 2. If you remember, it's the same, will be the same output impedance for the case of common source with degeneration. When there was an RS degeneration, and exactly we'll find it in the previous lectures. So we will have R out 2 here equals basically RS plus GM1 times R out 1 times RS plus R out 1. We have derived again this one earlier. So if it was the amplifier just having, this is Vn, this is our output, and we want to check the R out here, then R out will just be the R out small of the amplifier. But the addition of higher output impedance, and that's something useful for many applications. Oh, again, we're having this issue. So R out equal 1 plus G R, sorry, the parenthesis is here. Okay, now what about if we replace the RS with another transistor that's acting as a current source? So RS will be replaced with R out 2 of that transistor M2. Why R out? We are connecting M from its drain side. That's why we are down. That's therefore the output impedance R out will be exactly the same as previous, only we are replacing the R out 2 will be instead of RS. So we will have R out 1 plus GM 1, R out 1, R out 2 plus R out 2. And you can approximate R. I don't know why I still have this issue. Okay, I will again fix these before uploading the slides. Okay, so this is what we just said, that the R output impedance will be approximately GM R out 1 multiplied with R out 2. And if R out 1 equals to R out 2, so it will be almost GM1 R out square, if they are equal to each other. Okay. Now let's take this example. We want to design an amplifier. Basically having, and we want them to get to give us an output impedance of 500 kilo ohm. And we have a current here equals to 0.5 milliamp. We want to assume that M1 and M2 in this figure, they are identical. Means they are W over L. They have the same W over L. This is meaning of identical here. And we assume that mu1 COX equals 100 microamp per volt square. And we assume lambda equal 0.1 volt inverse. So again, since they are identical, this means R out 1 equals to R simplicity, and assume that the output impedance equals to GM, R GM1, R out 1, R out 2, which is basically GM1, R out square. And this equals to 100 kilo ohm. And so this is equal to G. Remember the definition of R out is 1 over lambda ID. And lambda equals to 0.1 and ID is equal to 0.5 milliamps. So therefore R out will equals to 1. And again, R out 1 will equal to R out 2 because W over L of them, they are the same and they are identical. So now from here we get GM1 equals to 1 over 800 ohm inverse. From here we just replace the R, we repeated, and we remember that the relation of GM equal to mu1 COX W over L times ID, and putting this 1 over 800 equals to 2 times 100 times 10 to power minus 6, the mu1 COX times W over L, which we want to find, and times 10 to power minus 3. From here, we get W over L after doing the math. You will, and that is the design. So now you size your transistor with this sizing. Whatever you select, minimum or whatever size of L, you will select W or, to have this W over L with this ratio in order to get this output impedance that you are looking for. Okay, now we can also have the cascode with the PMOS devices, not only. Somebody's asking, how did I obtain this value for GM 1 over 800? Ideally, from doing the calculation of this, this equation here. So we replace the R out square. So 500K equals GM 1 multiplied with 20K square divided by 4. 5 divided by 4 ideally will give me this 1 over 800. If you do the math, you will, I mean, with a calculator, you will get the same value. So it came from this equation. I mean, I have the values calculated from the book because this is example. So I calculated myself, but ideally it should be it is coming from this relation, and hopefully the value is correct. If there is any issue, you find the calculation, let me know and I'll fix it on the slides. Okay, now we can also again have the PMOS to give us the same output impedance using the Cascode. So it will be exactly the same. Now you just need to make sure that the, let me write to GM, almost GM1, R out 1, R out 2. Now you need to remember that the GM is of the one that is first you are looking through it. So if it was here called GM2, and so this is M2 and this is M1, it will be GM2 down here, but it's not the case. So the first is the transistor, the GM of the first transistor that you are looking for. And the one connecting on the source side of that is our RS originally. Again, all this will be fixed. Okay, now my mistake. I mean, this is not I, that is basically M1. So how this is basically the output impedance will be, so it will be something like this. This is RP in parallel with R out 1, and we have down here R out 2. Okay, so the M1 again of transistor of the one who's up multiplied with R out 1 in parallel with RP plus R out 2 plus RP in parallel with the R one. With the RP. Is it clear why it's appearing in parallel? Because it's connected from both two terminals, from the source to the drain of the transistor. That's why it's appearing in parallel with the transistor R out 1. Now let's do these further examples in order to help get the concept. So these are from the book's question at the end of the chapter. So let's start with that, and we have a diode connected transistor M2. Will the presence of have to be, if you have a guess, you can tell me, otherwise I can tell my own guess. Okay, no guesses. It's not going to do any harm effect to us. I mean, it's not going to change the impedance that we see from this diode connected transistor in the gate path. And here, there is no current come here because this is the gate of the transistor. Therefore, it's not going to do anything for us. It's like it's not existent. That's why what emitted, so we will see 1 over GM2 in parallel. It will look something like this. This is R out 1, and the down that we see is basically two. They don't, I mean, I should draw here. Yeah, my drawing of the previous one here, I forgot to add the GMV1, because otherwise it will look like they are appearing in series with each other, and that can be confusing. I don't want you to get confused on this. Out 1. Multiplied with R1 over GM2 in parallel with the R out 2 plus R out 1 plus 1 over GM2 in parallel with the R out over the R2. Okay, so again, this is the GM times R out times the RS and plus the R out plus the RS. The same, if you know, again, I'm reminding you with the standard relation for the cascode impedance. GM, R out, RS plus R out plus RS. Okay, so this is what we just did exactly here. Now for part B, now again, what about this connection? VB1 is shared between voltage. I mean, it doesn't matter for us whether they are the same voltage or they are biased through the same voltage or with different voltage. Both of them, they will be end up with 0 in the small signal model. So they are not going to be any different for us. So what we are seeing, our RS here is R out 2. So R out 1 plus R out 1 plus R out 2. So RS here is replaced with R out 2. Do I have anybody's asking? Yes, somebody's asking about RG. RG in the part, there is no current flow of the for it's like it's not existent. Because and in the previous class, I derived the impedance if RG was there. It is going to matter because there is a voltage drop across there because ID following there. So we have to be careful where is the location of RG. Okay, now let's see example C. If anything still remains unclear from my answer, please let me know. Now in part C, what do we see? We see that we have M1 and M3, they are in parallel with each other, and down we see M2. M2 down is, so our RS is basically R out 2 because we are seeing M2 from its drain side. Okay, now, however, there is something different here for when we have both transistors, they are in parallel with each other. So what is this difference? Let's do. Since those transistors, they are appearing in parallel, so both of them, they give us current. And therefore, the GM gets added while their output impedance basically become in parallel. Means if you look, you have two current sources, one from GM 3, V1, let's call it, and this is GM 2, V1, the same. Impedance are out, and this one, so this is GM1, sorry. And this has an impedance R out 3. Isn't this equal to having an R out 3 in parallel with the R out 1 and a collective V1? This is drain and this is this. I mean, I have question mark on this. Isn't it the same? So when we have two transistors, they are in parallel with each other. Since they both, their equivalent circuit, they both have in this direction, in the same direction, and in parallel with an output impedance. So it will be equivalent to a single current source, that is GM, the summation of their GMs, and in parallel with a resistor, that equivalent resistor, which is in parallel there times R out 3 in parallel with the R out 1 times the RS, which is down R out 2 plus R out 3 in parallel with the R out 1 plus R out 2. Any question on this? Is it clear? Okay, no question. Now let's do the part D. In part D, and here the answer basically assuming that the GMR out, yeah, since GMR out much greater than 1, I forgot about this. You can assume, I mean, ignore those two parts. Only remember use GMR out RS. You can make this. Now, what about the last example, which is basically let me draw our first transistor and connect to the second one. Here, grounded, and so this is VB1, and the output of this one, the drain is connected as the gate of the second one. This is M1. So this one is quite tricky because you cannot assume that you are seeing down here an R out because the gate is not grounded. Again, we cannot make the assumption that we are seeing here R out 2. Why? Because the gate is not grounded of this one. It's connected to the wrong. How to get the correct answer? You need to the output impedance by shorting the input and basically applying a test source from the R outside. So we need to draw the small signal model. So this node is going to be grounded. So this is a ground. This is gate of M1. And we connected to the drain of M2. So we will have R out 2. And then there is here GM times V1. Let's call it V2. And we have here basically another, we will have R out 1. And from this side, we are applying the test source. Now let's identify where is the current source and it's basically defined between those nodes, the gate and the source. V1 is defined here. Now, what about V2 for this transistor? The gate is connected to the drain of M1 and the source is grounded. So where is the drain of M1? It's here. So this is between the positive side and because the gate M2 is connected to the drain of the first one. And this is here the drain of M1, source of M1. And this is the drain of M2. Therefore, the gate is also shared here of M2. So now we want to find the output impedance of this one is with our I test. Okay, so now I test is basically equals to what? Current that is going in this direction. So I test equals to GM2 times V1 minus V1 divided by R out 2. So 1 second. GM2. Yeah, why is this? Can anybody tell? And this is 1 second, I'll tell you. GM1 equals to times V1 plus. So why all this is basically are trying to write KCL at these points in order to find how much current is going through that. And then we are simplifying it in order to get the ratio of the Vx over or V test over I test. So after that, what we will do, we need, basically here we are making sure that what is the direction of the current. So if you are assuming it in this point or here, so here the same, I mean, total at this, if we make it like there is a wire in the middle. So they will be making here I test again. Just make sure this thing. Okay. So you can do, I mean, this simplification, it's going to take some, then I can explain it again. But what at the end, get GM2. All of this is just replaced by 1 over GM2. So it's quite surprising that this entire impedance is just 1 over GM2. I mean, there is, you need to use your KCL tricks. So it was the of the output and for us, which is called the short circuit transconductance, which is basically meaning how it's called capital GM, and it tells us how much our circuit can be good in giving us or in converting our input voltage into output current. So the same way the small GM was related to a single transistor, here the capital GM find this relation with respect to the entire circuit that we are having. Okay, so now, yes, find this capital GM of our circuit by having our finding the ratio of our output current divided by the input voltage when we are shorting the output. So it is I out over Vn when V out is equal to 0. This is the way or capital GM of our circuit. So here, like we are shorting the output and finding what is I out when basically there is what is I out divided by V in. Now, when I short this output, if we look at the small signal model, this is R out, and this is the source, GM times V1 and from here is Vn, this is V1, and this is V out. Okay, if I short V out, this means this is grounded, and the I out is in this direction. Since both sides of R1 is, this is a ground and this is a ground, there is no current is going to come in R out one. So all I out will equal to GM times V1. And as previously, V1 is equal to Vn. So Vn over I out, sorry, I out over Vn when V out equals to 0 is just equal to small gm. So capital GM equals the resistance of just M1 alone. Okay, this is not so important. Yeah, I'll fix these slides. Okay, now what we want to see here, basically, how from with the help of the Cascode, how we can get more, we need to know that the gain is basically minus capital GM times the R out of any amplifier. This is another way of finding the gain, that the gain of the amplifier is equal minus transconductance of the circuit multiplied with the output impedance that you are seeing at the output here. We can prove that it's similar thing to what we did before. We need to short the output, find the I out over Vn, and it will be end up equal to the small gm of transistor M1 because it's coming from here. I mean, you can do the proof that this is correct. And the R out, since up we are seeing an ideal current source, it will have an infinite impedance. What about down? Down we see a cascode that has an impedance of GM2 times R out 2 times R out 1. So the entire gain of the circuit will be minus GM1 multiplied with the output impedance, which is GM2 R out 1 times R out 2. Okay, any question on this? No questions? Another cascode stage that basically we have
a question.
Zahra, yes.
Ma'am, in the last slide, how did you,
sorry?
the expression for the gain, how did you find that?
This minus here that they replace their Norton equivalent. You have an R out and then an I out, and their V out equals I out times R out, and I out is itself capital GM times Vn. Okay, then from here you simplify that V out over Vn is it clear?
Yes, ma'am. Thank you.
Thank you. Sorry that I skipped this slide. I thought I'll just tell you here and no need to prove it. Okay. Again, basically, so in most of the circuit, we will be having that the capital transconductance is equal to the small transconductance of the main transistor in most of the circuit. I don't want you, like there are some other deriving this one. I just want you to get the bigger picture of the things and not we just stuck in doing sense. So Vn equals minus Gm1, the Gm of the main transistor where Vn is coming on it, multiply R out, basically up, and we are seeing something down. So, and the R out will be the parallel combination of them. So it will be R out P in parallel with the R out and direction. Okay. And then, so R out P is a cascode of the PMOS that's equivalent to GM3, R out 3, R out GM2, R out 2, R out 1, the another cascode of the NMOS devices. Therefore, our gain will be minus GM1, GM3, R out 3, R out 4 in parallel with the GM2, R out 2, R out 1. Similar to this, you need to be able to solve it. That does not require much of a small signal model drawing. By just looking, you need to be important. Okay. Any question on this? Did anybody did not get this example? I just want to make sure that everyone got this. I don't be lost on something. Any question on this? Okay. Now let's do an example. So we have here a cascode amplifier that is basically W over L of transistor 1 and 2 equal 30, W over L of transistor 3 and 4 equals to 40. The IDs of all the transistors, they are the same and they are equivalent to half milliamp. We're given mu1 COX equal 100 microamp per volt square and mu P COX equals to 50 milliamp and lambda n 0.1 volt inverse, lambda P 0.15 volt inverse. We need to decide the voltage gain. So minus GM3 R out 3 R out 4 in parallel with the GM2 R out 1 R out 2. Now when the question is basically asking you of the transistor, you need to find the currents, you need to decide what are the gain, all the things that are missing. If the question was asking for a design, usually you need to find the size of the transistor, but here the question is asking to determine the voltage gain of the amplifier. So we have this equation or this relation for the voltage gain of the amplifier. Since the sizes of M1 and M2, they are the same, therefore GM1 will equal to GM2. And similarly, GM3 will equal to GM4 because the current is the same through them and their sizes is the same. So therefore, the GMs will be equal to each other. And the GM is equal to 2 mu n COX W over L times ID. And we know mu and COX, we know W over L, we know ID. They are all given for us in the equation. Okay, so once you will plug in all these values here, you will get the value of the GM. Again, it's calculated in the book. I didn't calculate myself for the time. So this is 1 over 577 ohm inverse. Similarly, we can find GM2 and GM3 to mu P X unit P most 2 W over L of transistor 3 and 4 times ID. And this will come out to be 1 over 707 ohm inverse. So we have calculated GM1 and GM3, and they are equal to the other. Now from here, what we can find also, can find R out of 1 and 2, it's equivalent to 1 over lambda n times ID, and this becomes 20 kilo ohm P times ID, and this comes out to be 13.3 kilo we need for calculating the gain. So AV will equal minus GM1 is 1 over 577 times GM3 is 1 over 707 times 13.3 square in parallel with 1 over square, because the R outs, they are the same, and this comes out to be minus 318. So this is the gain of the amplifier. Any question able to do such example? Any question? No question. Yes.
In the improved MOS Cascode amplifier, how does the gain
Yes.
improve?
A Cascode amplifier. You, if you remember, if we have just like this, and V out here, this is an amplifier, a common source without, and here I'm biasing, this is 2 minus GM1 times R out 1 in parallel with the R out 2. Okay, so typically GM, I mean, this is the gain compared to the gain that we are having here. This one will be much larger than the down one, because the output impedance than the cascode impedance.
Thank you.
Zahra, is it clear?
Yes, ma'am.
Okay, thank you. And this is it. Okay. Now I'll do a few more examples. First, I think we have just examples. This circuit, which is here, we want to find the output impedance that we are seeing here, R out, when we can assume that all transistors, they are operating in the saturation, and okay, here I to ignore the RS. So again, will be just M1 times RS plus R out 1. So here, meaning ignore the other two terms when you given this assumption, the GMR out much greater than 1. Okay, so here we will have R out equal, yeah. I have any effect of this RG? No. Why? because again, RG is on the gate and no current here. So it's like no current, no voltage drop, no change. Again, no current, no voltage drop, no change. Okay, drop, there is a changes. Okay, now we need to just to identify what is our RS here. RS, since we are looking from the source of M2, we will see 1 over GM2 in parallel with the R out 2. Okay, and therefore my gain will be GM1 R out 1 times 1 over GM2 in parallel with the R out 2. Okay, now let's do this example. The same question is the same. Just my question, who is in parallel with the other? Do I see that M2 in parallel with the M3 or M3 in parallel with the M1? If you make the assumption that M1 is in parallel with M3, you will be wrong. Why? Because though this side is common, but the other side, this is a V, this is a drain of M3. Okay, so the thing is that we see the circuit equivalent. This is M1, this is VB1, and here we see from R out from M. Therefore, we will see, and our question is R parallel with R out 3. Is this clear to everybody? Okay, so our total R out will be GM1 times R out 1 times R out 2 in parallel with the R out. This is our again. So now we are looking from down here, and we are seeing one first, and then we say so we see out. And in M3, we are also looking from its drain side, so we will see R out 3. So it will be similar to the previous case. R out equals to GM1 times R out 1 times R out 2 in parallel with R out 3. And this was our RS. How to calculate this one? Are you clear about it, or is there any confusion? Okay, now see we have example. Okay, so now we have 3 transistors cascoded on top of each other. So our R, let's see what is our RS. Our RS is from down here. So our GM, and therefore the entire R out will be GM1 times R out 1 times our RS for it, which is GM2, R out 2, R out 3. Okay, let's see further example. Now here we want to decide the gain of the amplifier. In them times the R out. Okay, so minus GM1 times the output impedance going to be the output we see here. So it will be the impedance that we see down with the impedance that we see up. They are in parallel with each other. So times R out. And let's call this ROP, and this is RON. So R, the cascode through the PMOS. So it's GM3, R out 3, R out 4. And the RON is basically GM1 times what? Sorry, GM2 times R out 2. And this is what we discussed. We did this example earlier. So the total gain will be minus GM R out 2 in parallel with the RP times R out 1. Any question on this? Okay, this should be fine. Now, what about this example? Just take a second to look yourself at the circuit. So our GM is capital GM times R out. Now, let's find our R out. Our out, again, the impedance that we see up in parallel with the impedance that we see down. Let's do them one by one. This is R out P, and this is R out N. So R out equals R out and R out P is equal to GM3, R out 3, R out 4. This is easy. What about R out N? So we see so we will have GM2 times R out 2 times R out 1 in parallel with the R out 5. So the overall gain is AV out 4 parallel with GM2, R out 2, R out 1 in parallel with the R out 5. Any question on this? Are you following with me? Fine, clear? Okay, now this is the last example that we are going to talk about it today. So this question is basically asking us this cascode for a voltage gain of, we need a gain of 200. And we have a power budget of 2 milliamps. We have a supply voltage of 1.8 volt, assuming that all transistors, they have the same size of 20 over 0.18. So this is the size of all the transistors. We have lambda n equals to 2 lambda is equal to 2 volt inverse. So we need to find all the DC levels for VN, VB1, VB2, and VB3. So we need all these voltages. Sorry, no, we are given VB1 and VB2. This is a 0.9 volt given. Supply is 1.8 volt. Okay, so this is the first thing. We know how to like start from here. We know the power consumption. So power equals to VDD multiplier current that's drawn from the supply, and power is 2 milliamps, sorry, 2 milliwatts equals to 1.8 volts times ID. From here, I can find ID equals to 1 the current, and we also know we need to find the GM values. Okay, so we know also we have the voltage gain relation. Let's write the voltage gain relation. So AV equals to minus GM1 times the R out, is equal to GM2. Okay, and this is equal to 200. Equals to 200. So now if I know what is the value of the GM1, we can find out. Okay, so this is from here, the GM1 is 0. So we know size now we know the ID we can equal to 2, 4. And what else then we can find? Still, we need to find for GM. We are missing something here. Yes, there is something missing. Sorry, I mean one step that we need to find. Also, we know that the GM of the transistor equals to 2ID over VGS minus V threshold. So we can find from VB, yeah, there is something that what can we do? For VN level, if I put GM1 and I put 2ID, VGS transistor 1 is equal to its V input level. And now we will be just GM3, it's also 2ID over VS of equal to VDD minus VB3. So we can find the VB3 from here after you find all this GM. I don't know why they are doing all those steps in the book. Okay. Any question on this? Is there any question? Are you with me or I lost you somewhere? Okay. So just will give a brief introduction about this topic, but we will go into the details of next class. If you have any question about what we have covered so far, please let me know. So we will be, basically what we did is that we find how to calculate the output impedance and how to use that output impedance for finding the gain of the amplifier. Those are the two main things that you need to know. Now there is another concept in this book, which is basically about, or in this chapter is about the current mirrors. And the use of the current mirror is that we are mirroring the currents, or having extra copies of the same current or multiples of it without needing to have multiple current sources on chip. It's typically very difficult to, or costly, to have design it to be a fixed current value that does not get affected by the variations in the process or the temperature or any changes in the power supply. And these normally we refer to them as PVT variations. So you need to make a current source that is independent of these variations, and therefore you need to make a strong design that usually you don't want to mimic or to have it on multiple times on your chip. Therefore, there is some concept or some circuit, we call it a current mirror, that allows us to take copies of in the circuit for this one. Okay, so I think we can come back to it next time. And if you have a question, please let me know. And next class we will have as well. Please let me know. I can answer your questions.